Hello everyone, myself Uday Ranjan Gaur, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology, Hyderabad. I am here to teach Aerospace Vehicle Structures II course, which is a core subject in BTech or BE Aeronautical and Aerospace Engineering. So therefore, before we go into this particular module, we have to make sure that there are some prerequisites for the subject. That those prerequisites are engineering mechanics, mechanics of solids, aerospace vehicle structures 1, and these fundamentals will be used in this present course. And let me share my presentation with you guys. Yeah. So Aerospace Vehicle Structures 2, and the course code is A4AE13, and this is module 1, which is introduction we cover in this particular. So the prerequisites, as I mentioned, engineering mechanics, mechanics of solids, aerospace vehicle structures 1, and engineering mathematics. This is very, very important, engineering mathematics, because here we have a lot of derivations as well as problems. So the use of mathematics is very, very high in this particular subject. And there are 5 course outcomes, and based on which the course is designed. And the first one is to illustrate at the end of this course, the students are able to illustrate the tension field and action flow diagrams. Second one, explain the failure stresses in plates and stiffened panels. Third one, demonstrate a shear loaded thin wall beams, so general stress strain and relationships, displacement relationships, direct stress and shear flow system, shear center, as well as twist and warping. The fourth one, the students can be able to differentiate between buckling of thin plates and deflections due to bending. And the fifth outcome, students can be able to develop wheel spars, box wheels, tapered wheel spar, and open and close section wheels. If you see syllabus, which is there in this particular course, there are 5 units, and unit 1 is thin plate theory and structural instability. Unit 2 is buckling of thin plates and bending of thin wall beams. Unit 3 is shear and torsion of thin wall beams. And Unit 4, structural idealization of thin wall beams, torsion of thin wall beams. And Unit 5, stress analysis of aircraft components. So that is wing and fuselage. So each unit have 12 classes. 11 classes plus 1 is a practice class. These are some textbooks and references which are given. So 3 textbooks and 4 reference books are given for your understanding as well as reference. So here in this we have 11 modules. So in the present module, in unit 1, in the present module we'll cover introduction part. So in this present module, we have 2 learning outcomes. The first one is the students are able to differentiate plates of various thicknesses. In the second module, the students are able to analyze the application of thin plates. Thin plate is nothing but a sheet of material whose thickness is very, very small when you compare with its lateral dimensions. So therefore, because it is very thin and it's being used extensively in aircraft and aerospace industry, and for any aircraft design or aerospace vehicle design, the minimum weight is the paramount design. So therefore, we always look for minimum weight in the structures design. So therefore, this thin plate, which has minimum weight yet has more strength, will be used more extensively. And it may be between the stringers, or it may be between the frames in the fuselage. Okay, so these thin plates can be used most widely in most component of aircrafts. And it is theoretically, there is a particular ratio based on which we classify plates as thin, thick, and membranes. For example, if the ratio of dimension of the plate to its thickness is less than, that is, if it is between 8 and 80, these plates are called as thin plates. If the ratio of B by T is less than or equal to 8, these are regarded as thick plates. If the ratio of B by T is greater than or equal to 80, then these are called membranes. Okay, and also these thin plates can be applied in different specializations like aerospace, marine, civil. So therefore, we make use of the thin plates for our studies in this particular structures. Now, if you see this one, these are the thin plates, and the right side diagram is nothing but the schematic diagram of the thin plate. And you can see the axis system, x-axis, y-axis, and z-axis taken in the below direction. And the plate dimensions are considered as A and B, whereas thickness is very, very small and it is depicted here as small h. Okay. And in this chapter, we investigate two types of problems, approaches. So first approach is an exact theory based on the solution of a differential equation. And the second approach is energy method, which relies on the principle of stationary value of the total potential energy of the plate and its applied loading. So in these two approaches, we see what are the loads we are applying and what is how the plate will behave under that particular loading, and probably we may find the expressions for the deflection of the plate. And the assumptions for thin plate, there are five assumptions. Material of the plate is elastic, homogeneous, and isotropic, and the plate is initially flat. The deflection of the midplane is small compared with the lateral the thickness of the plate. Plane sections remain plane even after bending. Since the displacement of a plate are small, it is assumed that the middle plane or surface remain unstrained after bending. So these are the assumptions of filters which we consider in this particular unit. Okay, so this is your introduction class, and we move on with the next module, that is plates subjected to bending, in our next discussion. Thank you everyone for listening.